All right, so I think we are connected. Let me just double check. All right. Um, so the YouTube live stream is also on. So if you click on that one, it should show that it is recording. We have another. Oh, we don't have a whole lot of time left. Less than a minute. But I think I'm ready to go. Oh, live streaming on this side. Yep, I'm going to live stream through Discord too. Thank you, Nick, for reminding me. So let me grab the OBS screen. There we go. There we go. All right. So I got the I got the Discord live stream turned on, so you can interact more in real time with me. And I also have the YouTube live stream turned on just for recording purposes. So I think I'm gonna get started with the class. Um, so the good news and the bad news. The good news is I got more questions graded, and the bad news is I have not gotten every single question graded. So the last question is still ungraded at this point, but I got 4 out of the 5 graded at this point, and I think I can get the last one graded sometime tonight, probably after 7 p.m. or so. So there's that. I also spent the entire spring break, doing my own coding so that I can use a program to generate variations of questions for the upcoming exam too. And I'm going to probably use similar coding techniques to generate questions for the final exam. So the idea is to generate questions that are different and yet they have the same kind of difficulty level. So that's kind of fun for me. After the class is over, if anyone is interested, I can share some of the code or the tools that I use to generate the code. There's a whole lot of JavaScript programming because I wrote everything in JavaScript in this case. All right, so with that out of the way, I did post 2 questions, on the Discord channel, on the general channel, just so that you guys have something to gnaw on. So I'm switching back to the general text channel right now and read some of the questions. Um, the first one was, how come we cannot find a relation for a set that only has 3 elements, that is reflexive, not symmetric, and not antisymmetric, and also not transitive? So I'm not sure whether anyone has given this any thoughts, and if so, you can go ahead and share your answer with the rest of the class if you want to, or you can also start a discussion to talk about your solution to that particular question. The second one is a little bit more canned. The second one was actually part of what my program can generate. It has a psi, which is everything that is known to be true, and it also has a phi, which is the proposed statement that we want to see if it is a theorem or not. So with this one, you have to do the same thing as the homework assignments, where you have to take psi and then turn it into a CNF. You have to negate phi because that's the proposed theorem, and in proof by contradiction, you have to negate it first. Then you combine the CNF corresponding to the negated phi with the CNF of psi, and then with those two concatenated, then you perform resolution, and you can stop your resolution when you get to a point where there are no more possible resolutions, or you can stop when you have reached a contradiction, which means a false or a zero is the result of one of the resolutions. Several people asked a few questions about resolution over the break, which is great. And the idea is, even though I do it in a particular way, which is left to right in a more systematic way, you don't have to do it that way. So, in other words, you can do it in any way you want, as long as it gets to the point where you have nowhere else to go in terms of resolution, or you get to the contradiction and then you can stop. Okay. All right. So I got a few people typing, but I don't see anything actually logged in the text channel. So I'm gonna continue with the other topics for today. So do we have any questions before we proceed to talk about the topics that we left hanging before the break, which is the birthday problem? No questions?
Carol did actually type something in general.
In general? Oh, okay, now I
Yeah.
see it. Okay. Let's see.
Thanks.
Oh, thank you. All right, so let's check Carol's solution. Uh, it has to be reflexive. So I see 1 1, 2 2, and 3 3, so that's good. It has to be not symmetric, so that's pretty easy. I see 2 1 1 2, and then only 1 3 without a 3 1, so it is not symmetric. It is not supposed to be anti-symmetric. So if we have not anti-symmetric, that means we have, okay, in this case we have 2 1 1 2, and 1 and 2 are different, so it is not anti-symmetric, and it's not supposed to be transitive. So we got 2 1 1 2 1 2 2 1, that is still transitive. Then we got a 1 3. It is transitive, I think. So we have 2 1 1 3, but no 2 3. That is correct. Okay, very good. Okay, so we're using 1 as a bridge. Yay. Okay, so all right, cool.
Really, what I thought it was impossible since I figured we were counting the tuples that were reflexive with the 1 1 2 2. Um, Given that precondition that the relation has to be reflexive, I figured since that is the case, it would be impossible for it to also not be symmetric and not be anti.
Okay, so do we see why it is not okay, I'm going to put the Discord channel into view as well here, because this way I can highlight the answer. Okay, so in order for this to be not symmetric, okay, because not symmetric is one of the requirements here. So in order for this not to be symmetric, 2 1 1 2, is not gonna break that rule, but 1 3 does, because we have a 1 3 but not a 3 1. Symmetric says if 1 3 exists, then 3 1 has to exist if the relation um, is symmetric. But since 3 1 is missing, so the relation is actually not symmetric. So does that explain why the solution is not symmetric?
In a way, it tells me that we're not supposed to consider the tuples 1 1 2 2 and 3 3.
No, you can.
Reasoning behind why I found it impossible is because I was also considering. So if I have, say, x, or rather, yeah, x and y, 1 and 1, 2 or 3 and 3, we find that there is some. Um, oh wait, no, never mind. Right, right. We had to also consider
Right.
tuples
Yeah,
two
so
one one two.
yeah, so the important part is to make sure that you refer back to the definition of the qualification of symmetric. Because that for all, if I remember correctly, it's for all EF in X, and then in parentheses it says X R Y, excuse me, E R F, if and only if F R E. That is the definition of being symmetric. So all it's really saying is, if a value E relates to a value F in a particular relation, then in the same relation you have to find that F relates to E. Now, uh, if E and F are not related, then F and E cannot be related either. You have to remember the relations are unidirectional. So E, R, F, or E is related to F does not mean that F, R, E, or F relates to E. Is that
Right. I was just so caught up. I was just so caught up with just making a defined set of relations that is reflexive and just
mm-hmm.
adding nothing new to it.
Right, right.
So
Yeah,
yeah, like would
yeah.
just be one, one, two, two, three, nothing else.
Right. So the question is saying that being reflexive is a requirement, but it is not the only requirement. So in order for a relation to be reflexive, every element has to relate to itself in X. That's the requirement to be reflexive. But it doesn't say anything about can you have additional tuples relating elements to other elements. Does it kind of explain the answer? In other words, if you
Yeah.
okay, let me pull the Discord screen back up here. uh, right here. So in order for a relation to be reflexive, it has to have these three. Okay, if X is 1, 2, and 3, then R must have 1, 1, 2, 2, 3, 3 in order to be reflexive. But can it have any additional elements? Sure. I mean, if you have a whole bunch of other elements, it does not change the fact that it is reflexive. It just means that besides being reflexive, now you have some control over whether it is symmetric, anti-symmetric, and transitive.
Right.
Okay.
Yeah. Yeah. There's something in my brain thought it would be best to take the minimalist approach and just attach nothing else.
Right, right. The minimal
Yeah.
approach, means that you have something that satisfies the requirement of being reflexive, but you also have to remember that we also want the additional properties from this particular relation. So the question is, how do you break the rules for the other properties without losing, the reflexive property of this R? So
Right.
we okay, cool. So let me switch back to today's channel here. Okay. All right. All right. So what we'll do today is to talk about the birthday problem. So the birthday problem is usually it's basically asking what are the chances that you can look at it in one of two ways. Okay, you can say what are the chances that of a particular group of people, let's say our class, how what is the chances of no one shares a birthday with another person in class. The other way to ask the question, which is the complement of the original question, is what are the chances that two or more people share the same birthday in class. um, Note that I said two or more people share a birthday and not the same birthday, because you can have two people sharing one birthday and then another two people sharing another birthday and so on. So the question is, so it's better to look at it from the uniqueness perspective. What are the chances that all 50 people have unique birthdays? Okay, so we're gonna start reading this stuff here, okay, which is definitely a little bit dry, but we'll go ahead and look at this, okay, and particularly we'll look at it from the perspective of events, okay, and also we'll also look at it from the perspective of terms that we already know, which are experiments and trials. Okay, so what we do is we will look at a single trial, in this case as the birthday of a particular student. Okay, so when we so you can kind of imagine this as lining up everybody in class, okay, and then we look at each person and we ask, okay, what is your birthday, okay, and the person has to answer. We can look at that as a single trial. So if we look at asking a person for for the birthday as a single trial, then the experiment is really just going through the entire class and ask everybody in class what his or her birthday is. So do we have any questions mapping the concept or the concepts of experiments and trials to birthdays of students in a class? So okay, all right, so that's good. So when we look at it that way, we'll basically say the experiment has n trials, where n is the number of people in class. The outcome of a single instance of an experiment of a class of 3 students may look like the following. In other words, if I look at a single outcome, a single possible outcome of an experiment with 3 trials, it may look like this. Now you look at this and go like, but those do not look like dates. Well, that's because instead of using April 13th, I'm going to use the day in year to represent that particular day in the year. So this way we don't have to deal with dates. We just have to deal with integers. So that's explained in the next sentence, where each number in the tuple represents a day in the year. So do we have any questions about the representation in this case? How I am representing the outcome of an experiment that has 3 trials in this case? No questions? All right. So just to be kind of redundant, this is basically saying somebody has a birthday of January. Well, I didn't quite say whether it's zero oriented or not. If it's zero oriented, this will be January 3rd, and this would be January 5th, and this would be let's see. So 364 is going to be the last day of the year. So this would be 4, 3, 2, 1. So this would be the third last day of a year. So that's good. That's just a representation thing. So now, if we say, if we look at a class of 3 people, what would E look like? So, in order to understand what E is, we have to go back to how we define E. E is basically representing a subset of all the possible outcomes where 2 or more people share the same birthday. Okay, so we look at this E, which is a set of possible outcomes of this particular experiment, and we are interested only in permutations where 2 or more people share a birthday. Okay, so in this case, this 3 tuple is basically saying all 3 students in this class, have the same birthday, which is in this case, the second day of the year. The second tuple is representing the first 2 students share the same birthday, and then the third student does not share the same birthday. But not only do we know that the first 2 share the same birthday and the third one does not, we also know that in this case, the first 2 students, have January 2nd as a birthday, and then the third person has January 3rd as a birthday, and so on. So you can basically look at this list and go like, wow, this is going to be a pretty long list. Well, we know this is going to be a pretty long list because we are looking at everything that has non-unique items in a tuple. Okay, so any 3 tuple that has at least 2 items being identical is going to be on this list. Okay, and it's really hard to describe too. So instead of looking at things this way, it's better to look at things from the complement of E. So I fixed the spelling of complement. Instead of using COMPLI, it's PLE. So this is complement instead of complement. So the complement of E is basically, I call it F, and that's omega minus E. So now the question is, okay, what omega are we talking about? What is the set of all the possible outcomes? So does anyone want to chime in? Okay, because I can start up a mouse pad to try to explain that. So can anyone sum up what does omega look like in this case? We have a class of 3 people, and we are looking at the birthdays of those people, and omega is representing all possible outcomes of the experiment. It's the set of all possible outcomes. So if anyone wants to chime in, go ahead, and I'm just going to start up mousepad here so I can have a kind of virtual whiteboard to contain the discussion.
Is omega the number of ways that you can choose 3 people's birthday?
It is not the number of ways, it is the actual possible outcomes of experiments. So
Is it C 365 3?
it is not it's not C65.3. So let me fix the font size first because I had to change the font size for something else earlier. Okay, so when we look at omega of omega 3, which omega 3 here. So the 3 is a subscript. It is basically saying that we have 3 trials in the experiment, and then the parameter, or in this case the argument, is how many things can we choose 3. Okay, so in this case we have basically the first day, which is represented by 0 all the way up to 365. 4. There we go. So this set is interesting, but it's not what we're looking at, because what items are in this set would be something that looks like 1, 2, 3. It will have 3, 1, 3, 2, 1, 3, but it won't have 1, 1, 2. Okay, 1, 1, 2 is not going to be in this set. So can anyone remember why this particular omega? Well, okay. Um,
Would that
uh,
not be an E?
I take it back, because this omega 3 is specific to the discussion that we had earlier with the omega generator thing. So, let's go back to what Nick said, okay? So Nick said the combination, right? The C of 365 choose 3. 365 choose 3. And that's going to be a pretty huge number. But is this number representing the cardinality of omega? That's the question. Or, to be more specific, what is omega in this case? Omega in this case is the set of all possible outcomes, right? Okay, of an experiment of 3 trials. So now you have to look at this experiment and go like, well, is the nature of the experiment with or without replacement? That's my question. So let's think about this for a little bit, okay? So is this experiment itself, inherently, does it have replacement, or does it not have replacement for each trial?
I think it's with replacement. Oh, for each trial without replacement.
It is with replacement. Because remember, okay, so imagine this, okay? In your mind, imagine that we have a really small class with only 3 people, and we number these people, okay? First, second, and third, student in the class. So the question is, if I ask the first person, what is your birthday? Okay, the first person gives me a number, which is from 0 to 364. I ask the same question to the second person. The second person gives me a number within that range. And then I ask the third person, give me another number. The question is, if the first person already used a particular day in the year, can the second person have the same birthday?
Not in the same set.
It, why not?
Oh, wait. All possible. Okay, yes.
So the nature of the experiment itself is with replacement. Okay, because one person having a particular birthday does not mean that another person cannot have the same birthday. So it is with replacement. Okay, so let me just write it down here. This experiment is with replacement. Okay, so when we know that the experiment is with replacement, then omega is easier to express. So in this case, omega, which is still the set of all possible outcomes of the experiment, but because now we know the experiment is with replacement, then the omega is going to look like this. Okay, you can start with 0, 0, 0. Okay, all 3 people have the same birthday, which is the first day of the year, 0, 0, 1. And then we can have 0, 0, 2, and blah blah blah, and so on. Okay, so what is the other way to write this, right? I mean, we can say, oh, okay, so that means we are really looking at, the first person can have 0 to 364, and then the second person can also have 0 to 364, and then the last person, the third person in class, can also have 0 oops to 365, 364. Okay, the second one needs to be fixed here. Okay, does everybody see why omega can be expressed as the Cartesian product of 0 to 364, basically 3 times?
Yeah, so in that case, we're not looking at combinations.
we are not looking at combinations yet. Okay, so as far as the omega itself is concerned, we are not looking at combinations. So when we look at the set itself, okay, omega as a set is not very interesting in this case. Okay, we really just need to know the cardinality of omega. So when we look at the cardinality of omega, what do you think that's going to look like? Okay, we have 365 in the first set, and then we have a Cartesian product with another set that also has 365 elements. And then we do it again to the third set, which also has 365 elements. So what do you think is the cardinality of omega?
365 cubed.
Yes. Okay, so we are looking at 365 cubed. That is the cardinality of omega. Okay, given three people, we are only considering their birthday, okay, in a year, in whatever year they were born in. There are basically this number of ways for those people to have birthdays. Now, does it include things, cases where they are all the same? Yes, okay, but it includes every single way that they can have birthdays within those three people. So are we good with this one? Yes? Okay, so let's look at the original E. Okay, so the way I describe E is um, the number of, not the number, this is the set of all outcomes where at least two students share the same birthday. That is how E was defined. Okay, so that's why, in the text, one example of E is, I can use the same thing, 0, 0, 0, 0, 0, 1. We can have, 1, 1, 0. We can have, a whole bunch of stuff over here. So any three tuple where at least two of the items in the three tuple are the same will be in this particular E. Is that okay?
Makes sense?
Okay, all right, cool. But to compute, but we are not really interested in E as a set. We're only interested in the cardinality of E, because when we divide the cardinality of E by the cardinality of omega, that will give us the probability, which is the bottom line. Okay, we're only interested in the probability. So we don't need E exactly. We just need the cardinality. But E is not easy to compute. Okay, it's because it has, for three people it's relatively easy. But once you have more people, it's harder, because if you have four people, then you can have the first two people having the same birthday, the second two people having the same birthday. You can have the first person and the third person having the same birthday, the second and the fourth people having the same birthday. You can have the first and the fourth having the same birthday, and the middle two having the same birthday. So now it gets a little bit cumbersome to express. You can also have three people having the same birthday. You can have the first three having the same birthday. You can have the last three having the same birthday. You can have the first one and then the last two having the same birthday. You can have first two and the last one having the same birthday. So you can see how that can get out of hand, pretty quickly. So now what we want to do is to say, okay, that's really hard to express. What is omega minus E? Well, we call that F. But what exactly is F? F is the set of all outcomes, oops, where everyone has a unique birthday. Now that turns out to be pretty easy to express. F is actually much easier to express. So when we look at F, okay, what does F look like? F is going to look like something, it is still a set, it still has to be a subset of omega, because we are looking at a subportion of all the outcomes of the experiment. But it's going to have something like this, okay? 0, 1, 2, okay, nothing is shared, that's good. 0 to 1, 1 to 0, and so on, okay? So F is going to contain every single one of the three tuples in omega, where all three numbers in the three tuple are different. So are we still doing this, still understanding the symbols okay in this example? Are we good?
Yeah.
Okay, excellent. So now the question is, well, we can spend all day, trying to figure out, what f is going to look like, but at the end of the day, this is all we really care is, what is the cardinality of f? So when you look at the cardinality of f and you look at the composition of f, we can see that this is not a set. This is a 3-tuple. Because if this were a set, then we wouldn't have this one as a second element, because the set that contains 0, 1, and 2 is the same as the set that contains 0, 2, and 1, because in the set the ordering is not significant. So what math functions do we use to compute? We have 365 to begin with, and then we have 3 trials in the experiment. What is the total number of permutations? And guess what? This time it is without replacement, because once the first person uses up a birthday, the second person cannot use the same birthday anymore, because we put this artificial restriction to f because that is what we're interested in. So can someone tell me how to compute, or what function do we use to compute the cardinality of f? So let's look at our choices. Okay, this is how we can we can start the thinking process. We have the power function. Okay, something to the power of something else. We have combin. Okay, and then we have permute. So these are all correct names in the spreadsheet, and we know all three of these have something to do with computing the number of possible outcomes. Okay, so now the question is, which one should we use, and why do we choose that one? Okay, so we look at power first. Okay, and we say, no, that is not correct in this case. Why is it not correct? Why don't we use power in this case? Why can't we just toss it out right away?
The only power we really know for sure is just omega, the cardinality of omega.
Yes.
65 cubed.
But why do we use power in that case? It has to do with the nature of with replacement. With every single trial, each trial has 365 possible outcomes. And that's why we can use power. It is with replacement. Okay? But in this case, when we look at f is clearly without replacement, because that's what we are interested in. We want f to represent the set of all outcomes where everyone has a unique birthday. The word unique is pretty much suggesting that we are looking at without replacement in terms of the sequences of trials. Is that okay? Does everybody kind of catch this? Because you can look at certain words in English when we describe a problem and then say, oh, okay, that word is strongly correlated with this kind of property when it comes to the set of outcomes. So when we look at the word unique, okay, it really strongly suggests that we are looking at without replacement. If one trial has used up a particular choice in a set, that choice is no longer available to all the subsequent trials. Is that okay?
Yeah.
Okay.
It looks like we might want to use permutation then.
Yes. So now between combination and permutation, how do we differentiate between those two so that we can find the right choice? Okay, so I'm removing power because it is not applicable anymore. So we look at combin and permute, and then now we ask, okay, how are those two different? So does anyone want to help recall the differences between these two? I'm not interested in the actual formula. Okay, I'm looking into the concept. What is combination counting and what is permutation counting? Does anyone want to chime in? Okay. All right. So with combination, we are looking at possible outcomes, but the ordering is not important in the outcome. So a good example of using combination is lotto. Okay, because the way they draw the numbers from the basket, the ordering does not matter. Okay, if they draw the numbers in the sequence of 5, 6, and 2, it's considered the same as drawing those numbers in the sequence of 256 or 652 or 526 and so on. So in those cases we use combin because we are looking at the outcomes where the ordering of the values in the outcome of the experiment does not matter. Permutation, on the other hand, is basically saying, yeah, ordering does matter. Okay, so a very good let me think of a good example of permutation. That's not the birthday problem itself. Okay, so when we look at permutation, the number of possible routes, okay, is a permutation. Okay, um, so this is a traveling salesman problem. Okay, the traveling salesman problem is asking, how many ways can a salesman complete a tour of a particular number of cities? And the rule is that that particular salesman cannot revisit a city. Once a city is visited already, it cannot be revisited. And the person or then the salesman is starting from a location that is outside of the cities that the salesman has to visit. Okay, so in that case, permutation, um, hmm, well, it's factorial, but permutation is related to factorial in this case. So permutation, when we look at permutation, then we can say, out of this set of cities, the salesman can choose, a subset to visit. So in that case, it becomes a permutation. But in that case, ordering is important. Okay, so permutation counts tuples. So when we see that the event set is made out of tuples, then it is a strong indication that we are looking at permutations. So are we okay so far? How to differentiate combination and permutation and how to tell which one to use.
Can you say that one more time? About
Yes.
the permutation.
Okay, so in this case, when you look at permutation, okay, so when we look at permutation in this case, it is 365 choose 3. Okay, so what is that actually boiling down to? So when you look at permutation, it boils down to 365 factorial divided by 365 minus 3 factorial. Okay, that's the definition of permutation. But in this case, we can actually expand this to find out exactly what it's going to look like. Okay, 365 is a number that is unique to the numerator, so it's going to stay after the simplification. 364 is also unique to the numerator because the denominator doesn't have it. 363 is also unique to the numerator, but then 362 is common to both, because when you look at 365 factorial, it certainly has 362 as a component of the product. When you look at 365 minus 3, which is 362, and when you look at 362 factorial, pretty clearly, 362 is a part of it too. So that means, when we look at 1 all the way to 362, it is common to both the numerator as well as the denominator. So they all got canceled out. So after all the simplification, this is basically what the permutation of 365 choosing 3 is going to look like. But why does it look like this? Okay, so when you look at this, the question is, what is 365 representing? The 365 is representing the number of choices that the first person of the class can choose from, when we ask that person, what is your birthday? 364, in order for the birthdays to be unique in F, 364 is basically saying, oh, the first person has already taken up this particular day. The second person cannot use that day anymore, and as a result, there are only 364 choices left for the second person. And that basically also explains why the third number is 363, because the first 2 people have taken up 2 days already. They have circled 2 days in the calendar. The third person cannot use one of those two days. In Naturally, yes. Okay, so naturally, people can have the same birthday, but that particular three tuple is not going to be in F anymore, and as a result, we are not going to count it. In order for something to end up in the F event, um, all three numbers in the three tuple, they all have to be unique. Is that okay?
Yes.
Okay. So we don't want to use combination in this case, because if you look at combination, okay, how does it boil down to? Okay, it boils down to 365 factorial divided by, okay, so in here, but now we have two components in here. The first one is 365 minus 3 factorial, which is the same as the permutation, but the second one is 3 factorial. The reason why we have this additional 3 factorial here is because when we use combination, it is used to count the number of combinations, and in a combination which is represented by a set, ordering is not important. So in order to look at all the different ways to arrange 0, 1, 2, as tuples, and basically fold all of those into one single set, there are 6 ways to do it, and that 6 ways is the 3 factorial. So that's why in this case, because we are looking at tuples, okay, because we are looking at tuples, right? So as a result, we are not going to use combin, and we're going to use the permutation. Is that okay?
Yeah, definitely.
Okay, excellent. All right, cool. So at the end of all this discussion, what is the probability? Okay, so what is the probability of f over omega? Okay, so let's focus on f first. In other words, we're just looking at the probability of everybody in class has a unique birthday. No one shares the same birthday, shares a birthday with another person in class. Well, the probability is really just the cardinality of f divided by the cardinality of omega. So we already know what f is. F is the permutation of 365, and I'm going to use n here because the general problem asks what happens when we have n people in class. And then omega is the power, and it is 365 to the power of the number of people in class, which was 3 in our specific case, but in the general case it is n. Are we doing okay with this number, with this equation here? Yes? No? Any confirmation? We got one.
Well, I'm on board.
Okay, so we are good so far. All right, so let's go ahead and take a look at what these numbers will translate to when we put it into a spreadsheet, because I think it'll be quite interesting to see how everything boils down to in a spreadsheet. So I'm gonna start up LibreOffice. I don't need to show the entire screen, so I can show just a portion of it. We'll have n on this side. Oops. And then we'll have the probability on this side here. Well, maybe we'll break it down to more components here. So we'll look at the cardinality of omega. We'll look at the cardinality of f in this case. We'll look at the cardinality of the original e, which is the outcome set of at least 2 people in class share a birthday. That's e. And then we'll look at the probability of f divided by omega, and then we'll take a look at the probability of e divided by omega, the cardinality thereof. Okay, so we can always start with 0, okay, because with 0, it's still defined. Okay, everything is actually still defined, even though it doesn't seem to make sense. Because if you look at a class that is empty and you ask, what are the chances that blah 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 blah, it doesn't seem to make sense, right? But it actually still makes sense from the numerical perspective, because in this case, this is just the power. It is the power of 365, which is the number of days in a year, to the power of the number of people in class, which is A2. So we say, yep, there's only one element in the entire omega. Why do we have this one element in the omega? What is it? What does it look like? It's an empty tuple in this case. It's not an empty set. It is an empty tuple. Look at it as an array that has no elements. Okay. So what about the cardinality of f? Well, we just worked it out. It's a permutation thing. So we have 365 things to begin with, and then we choose 0 out of 365 because there are no students in this class. So how many ways can we choose nothing out of 365 items? The answer is, well, actually, not surprisingly, 1. Does that make sense? Or not?
Yep.
It all makes sense? Okay. So what about E? Well, the cardinality of E, that's the whole purpose of F, is so that we can get to E itself. So this is really just looking at the cardinality of omega and then subtract the cardinality of F from it. So now it is 0. Okay. So when you ask the question, how many ways can 2 people have the same birthday in a class of no one? The answer is there's no way to do it because we don't have enough people. So it makes perfect sense that the cardinality of E is 0 because there's no way you can actually find that 2 people having the same birthday in a class of no one. Okay. So when you look at the probability, okay, it's really just the cardinality of f in this case divided by the cardinality of omega, okay, and this is going to be the cardinality of E divided by the cardinality of omega. Okay, so even when there's no one in class, okay, these columns are already starting to make sense, but in a kind of weird way. What if the class has 1 person? Okay, I'm going to say 1 more than the previous case, because in this case, I got all the equations using the relative cell references, so I can just do this to figure out the chances. Okay, so let's see whether this makes sense or not. Okay, let's first look at omega. Okay, both the value and also the expression expressing the cardinality of omega. So in this case, we are asking, I got a class of 1 person. How many ways can birthdays be arranged when there's only 1 person in the entire class? Oh, well, there are 365 ways because this person, the only 1 person in class, can have any one of these 365 days as his or her birthday. So it makes sense that the cardinality of omega is really just 365. When we look at F, which is asking how many ways can this person be unique in can have a unique birthday in the class? Oh, I made a mistake here. Okay, so let me fix that first. The mistake that I made was here, instead of using a 0, I should have made it reference this particular cell. So that was my mistake, and I think this one is fine. Okay, so let me just copy this again. Now it makes a lot more sense. This makes a lot more sense now because remember what F is representing. F is the set of all the outcomes where each person in class has a unique birthday. Okay, when you have only 1 person in class, then yeah, every single one of those choices, or it's going to be every single one of those outcome is unique because without at least 2 people, you cannot have 2 people sharing the same birthday. So every birthday is basically unique. Is that okay? Does everybody understand why the cardinality of F is the same as omega in this case? Okay, so when you look at E, it's going to be, the cardinality of E is also going to be 0 because no one is going to share the same birthday with another person. Okay, and then the ratio is just the ratio between this divided by this and also this divided by this, so it kind of makes sense over here. So when we get to 2, we can start to finally see something that is not too obvious. Okay, so we'll do the same trick. Okay, so instead of using 2, we'll just go ahead and duplicate this row. Okay, so now we look at this and go like, okay, what are we talking about here? We got 2 people in class. So with two people in class, we have 365 times 364 different ways in order for people to have birthdays in that class. Okay, so that turns out to be 133225. This number is I take it back. It's not permutation, this is a power. So this is 365 to the power of 2, or 365 squared, because the first person can have any one of those 365 days, and then the second person can also have any one of those 365 days. This is the number of total possible outcomes of the experiment. This, on the other hand, is counting of all of those possible outcomes, how many of those are unique. Okay, F is representing unique outcomes. So, well, if the person is choosing a particular day, the second person cannot choose that particular day anymore. So this is basically 365 times 364, which is turns out to be 132860. This one is really just the difference between the cardinality of omega and the cardinality of f, which in this case is 365. So when you look at this, okay, there's a really high chance that everybody still has a unique birthday when you have a class of 2, which really makes sense. And this is the probability of those 2 people having the same birthday, which kind of makes sense too, that it is a relatively small number. Do we have any questions about this one?
Nope. Sounds good.
Sounds good. All right. So we're gonna replicate this, okay? So because when we look at 2, n equals to 2, and it makes sense, then we can just go ahead and drag it down, okay? And we'll drag it down to about 50, okay? So we'll drag it down to. I used up 1 column for n for the labels and 1 column for the case 0. So I think we need to get to 52 for 50. There we go. So when you okay, let me format the numbers a little bit so that it's easier to read. Okay, and you guys cannot see past 30, so I'm gonna scroll up a little bit too. I want to format. There we go, and we'll just go ahead and use smaller numbers, a smaller value. It doesn't have an engineering option where the exponent can only be a multiple of 3. Maybe it does. Yep, engineering notation. Okay, that's good to know. Okay, click OK, and then I'm gonna move it up because the trend is most people do not expect this. Okay, so when you look at E, okay, column E. So column E is representing the probability of everybody having a unique birthday. So you can see how, when you have 1 person, it is one. When you have 0 people in the class, it's 100%, 100%, 99.7%, and so on. And as the number of people increase in class, the probability decreases, because it kind of makes sense that when you have more people in class, the chances of having a collision, so to speak, or having 2 people having the same birthday increases. So the chances of people having unique birthdays would also decrease. But it is not about the trend that it is decreasing that is surprising. It is how rapidly it decreases that is surprising. So by the time we get to 50, okay, so assuming a class has 50 people, the chances is now down to, this is not 30%. Okay, this is 29 point something times 10 to the power of -3. So we are looking at 3%, not 30% here. Does that surprise anyone? No? You guys kind of knew this is the case already? So when you get into a class, a relatively large class with 50 people, the chances that all 50 people have different birthdays is less than 3%. All right? So everybody is accepting this fact just fine?
I mean, it seems very low for just 50 people, but
Yeah.
I mean, it doesn't seem terribly outside the realm of possibility.
No, it is non-zero if that's what you're saying, if that's what you're referring to. It is non-zero, but it is pretty low. I mean, 3% is a pretty low number. Just intuitively thinking about it, it is really low, but that's how the math works out. So, in other words, if you look at the flip side, there's a 97% chance that at least two people in class share the same birthday. That is pretty interesting. Now, my assembly programming class has 70 students, combining two lab sections. So let's work that one out, okay? Because it's going to go even more extreme. So we need another 25 rows or so, another 20. So let's go to 72. All right, so it is less than 1% in that case. When we have 70 people in a class, the chances of all 70 people having a unique birthday is less than 1%. It is basically 0.8 of a percent. No, I take it back. This is my bad math again. This is actually 0.08%, because the previous one is already 0.1 of a percent. This one is 0.08 of a percent. It's less than 0.1% of a chance. So in my assembly language programming class, I pretty much know, for the most part, that at least two people in class share the same birthday, and there are only 70 people. Because most people would use the ratio of the number of people in class divided by the number of days in a year as somewhat of a rough estimate of that probability. Okay, so on this column, I can just give you that ratio so that you guys can see what I'm talking about. So if I just divide, well, we can focus on F here, which is the number of unique cases. So if I look at just n divided by, no, 365 minus n, which is here, divided by 365, the chances works out. Okay, let me move down here. So it has the same direction. It is a non-increasing, or basically it's a monotonic function. So when you compare column E and column G, you can see both of these are monotonic. The big difference is how fast column E is going to decrease and how slow column G is decreasing. So if you just look at the ratio, okay, based on the number of people in class, um, a layman or person who does not work out this kind of math would probably still guess that, well, there's a 90-something% chance that everybody has a unique birthday when you only have 24 people in class, which kind of makes sense from the intuitive perspective, because when you look at 24, okay, and you look at 365, you're choosing 24 things out of 365, and you're asking, well, what are the chances that all 24 things are unique? The actual answer is about half of the chance all of those things are unique. But intuitively, when people just use the ratio, they come up with with a number that is like more than almost twice of the actual number. So this is kind of interesting, because the intuitive answer is completely wrong. When we look at n, when n is large. Is that okay? Does everybody understand this exercise? How we basically choose to use, how we manage to decide whether to use combinations versus permutation, and how we actually compute the probabilities. Are we good here?
Yeah, makes sense.
Okay, all right. So the birthday problem is a good one to study because you don't have to take my words for it. Um, and if you guys watch televisions, especially PBS stuff, um, that's that's a phrase used by one of the shows. Does anyone know which one I'm talking about? I'm sidetracking here, of course. Okay, maybe not. Okay, but you can look up birthday problem. Okay, and I mean, just look it up. Right click, Google, and you can see Wikipedia also has a page on this one. So if you find my explanation to be, oh, that's really hard to understand, well, you can go ahead and look at some of the other explanations online because this is a well-studied problem, and you can even see that somebody has a graph here, and you can also see how when we have 70 people, see how it's almost like 1.0, the probability of at least two people having the same birthday is almost 1, is almost 100%, which is coinciding with, our observation. 24, 25 is about 1/2. Okay, that's also the same as what we have in our spreadsheet. So you can go ahead and look at, this one, if you're interested in a more in-depth or alternative treatment of the same subject. Okay, so are we good so far with example 1, which is the birthday problem? Okay. All right, so if we're good with this one, we're going to move on to example number 2, which is a different kind of problem. It is a coin toss problem. So a coin toss problem is looking at a series of coin tosses, and it's asking about the number of heads and the number of tails. Okay, so it's not asking about how the head and the tails are distributed over the trials. It is really just asking for the number. Okay. So we are going to take a look at some examples here. So the event set is all the ways that we can end up with 3 heads and 3 heads out of 5 tosses. So to end up with 3 heads out of 5 tosses, we'll have to include head, 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 tail, tail, head, tail, head, tail, head, and so on and so forth. So the question is, what is the cardinality of E in this case? Now, before we get to this point, we also have to look at omega. So with the entire example, we are looking at an experiment that involves tossing a coin 5 times. And we assume that the coin can only land on a head or a tail, so it cannot land on an edge and rest on the edge, so it can only land on a head and a tail. And the question is asking, what are the chances that we end up with 3 heads and 2 tails? Okay, that's what we are asking. So now we have to basically look at this problem and look at omega. So omega is 2 to the power of 5. So because when you look at how many different ways can we end up with heads and tails, each toss, okay, each coin toss has 2 possible outcomes, head or tail. But when you look at the second toss, it also has head and tail. In other words, we are looking at a case where there is replacement. Okay, and because there is replacement, so we're only looking at a power here. So if you want to kind of visualize, omega, what it looks like in this case, so omega in this case is going to be head, tail, Cartesian product with head, tail, Cartesian product with head, tail, Cartesian product with head, tail, and guess what? One more time. This is our omega. But we are not really interested in omega itself, which is a set that has a bunch of 5 tuples with heads and tails. We are interested in the cardinality of omega. So when you are only interested in omega, then we look at the cardinality of the outcome set of each trial, and then we take that and raise it to the power of the number of trials. So it is 2 to the power of 5 in this case. So do we have any questions about the omega for the coin toss example? No questions? All right. So now we can now start to focus on the other question. Okay, the other question is we're only interested in the ones with 3 heads out of 5 tosses, and how do we know the cardinality of that particular event? Okay, so does anyone have any idea of how to approach this problem? I mean, you can read ahead a little bit. The next paragraph basically describes how we cast this into a separate problem. So we can cast this into different problem because each item in a 5 tuple can only be a head or a tail. Now this is a really crucial part of solving this problem is each trial only has 2 possible choices or 2 possible outcomes for each trial. If it's not a head, it has to be a tail. If it's not a tail, it has to be a head. Okay, so that means instead of counting, 5 tuples, what we can do is we can characterize the 5 tuple using a set. So this particular set here is describing the same thing. This is a set of the indexes into items in the 5 tuple where that particular item in the 5 tuple is a head. Okay, so let me make sure everybody understands how we can make the transition from tuples into a set. So this 0 here is the index of the first head, which is this head over here. This 1 is the index of the second head, which is over here. And then this 4 over here is the index of the last head of the 5 coin tosses. So this is how we can represent the outcome of head, head, tail, tail, head in a 5 coin toss experiment, and we can basically encode it into a set of 0, 1, 4. Do we have any questions about this conversion? How we turn a outcome representation of 5 tuple into just a set of integers.
No, it seems pretty straightforward. Took me a
Okay.
second, but I got it.
Yeah, but this is only possible because each trial only has 2 possible outcomes. Because if it is not one, it has to be the other. Is that okay? So the absence of 2 and 3 over here is implying that those 2 are tails already. Is that okay?
Yeah, makes sense.
All right, cool. All right, so now that we are casting this problem into a set, then we can now think and go like, wait, hold on a second here. So this is the same thing as now asking, okay, because there are 5 possible indexes, 0, 1, 2, 3, 4, right? So there are 5 possible indexes. We want to choose 3 out of those 5 and put it into a set. That is, so if we can count that, how many ways can we choose 3 things out of 5 and put those things into a set? That will give us the same number or the same count as how many ways can we have a 5 tuple in which 3 of the 5 items are heads. Is everybody making that association? Okay, so I'm going to assume the answer is yes. If you guys need more time, don't hesitate to type in the text channel or just use the voice channel to let me know that, okay, I need more time. Okay, it's not a problem. All right. But that problem, okay, choosing 3 items out of 5 and putting those things into a set and ask how many ways can we do it, that's what combination does. Computes that, right? So that means now we can say, oh, we just use 5 choose 3 then. 5 choose 3 will give us the number of experiments, okay, tossing 5 coins, in which 3 out of the 5 tosses land on heads. Okay, so now when we look at the probability, which is E is what we're interested in, omega is representing the set of all the possible outcomes, then we are just looking at the ratio between those two, which is 5 choose 3 divided by 2 to the power of 5. Okay, So if you want to get a kind of better feel of what we're dealing with here, we can just do the calculation. Okay, so we can say uh, number of heads. Okay, and then we look at the cardinality of omega, and then we look at the probability. Okay, so we look at the probability of E divided by omega. So omega is going to be the same, for all of these cases. So really, everything is just 2 to the power 5, which is 32. So we just say, okay, 1, 2, 3, 4, 5, like that. The number of heads, okay, we need one more row because we can ask from 0 up to 5. So we need 6 rows over here. So in terms of the number of heads, we can have 0 because they're all tails. And then we just increment 1 at a time. So we have 0, 1, 2, 3, 4, 5, like so. And now we can compute the ratio between those two numbers. So we now have combin 32 choose 0, and then this whole thing divided by the cardinality of omega, and then we just drag it down like this. No, that doesn't look good. That does not look good. Something is not right. Oh, I know why. Because the reference to no, that should be fine. Okay, something is not right with this equation. So we have B2 32 choose A2, and then divide it. Nope, that's wrong. Okay. It's not 32 choose A2, it is 5 choose A2. Okay, so that was totally my bad. There we go. Okay, now it looks much better. So if somebody is to ask me, okay, what are the chances that out of 5 coin tosses that we get exactly 2 out of those 5 being heads? The answer is about 31%. What if it is 3 heads and 2 tails? 31% of a chance or so. Okay. So is that okay so far? Just looking at this table and how we come up with these numbers, and I can just click on one so you can see how the equation is set up, how the formula is set up. Any questions about this part? No questions? All right. So let's look at this from a slightly different perspective. Okay. What if I were to add up all of these probabilities? Okay, this is the probability of getting 0 head, 5 tails. This is the probability of getting 1 head, 4 tails, 2 head, 3 tails, 3 head, 2 tails, 4 head, 1 tail, and all 5 heads and 0 tails. If I were to add up all of these probabilities, what do you think they should add up to? Does someone want to take a guess? It's a number that we know very well. Yep. They become what? Okay, it kind of makes sense because that accounts for every single way that you can have an experiment outcome when you toss a coin 5 times. Okay, because you can only have 0, 1, 2, 3, 4, or 5 occurrences of heads for each experiment. Does that make sense so far? Any questions about this? No questions? Okay. So we can now expand this thing to something that's a little bit bigger. Okay. So we look at the number of heads. We look at omega again, and this time I'm going to be a little bit more systematic. Okay. Because I can now say let's look at n. Okay. So this time n is no longer a literal, and we'll make it a parameter. So we'll say, well, what if n is, I don't know, let's make it 10, okay? So now we can say the head is going to be, the first one is 0, the second one is 1 plus the previous one, Okay, and then in terms of omega, it's going to be the same thing, which is the power of 2 to the power of this thing here. And this time I have to be careful to use a dollar sign to say, when we copy and paste, do not change the row number. Okay, so we can just do this. And then when we look at the probability, it is now combin, and then we refer to this thing here again, but this time also remember to put a dollar sign here. This is the number of heads out of the entire experiment, this time of 10, and then divided by the cardinality of omega, and then we can drag in. So we need up to down here. There we go. All right. So when you look at these numbers, the first thing you might notice is it's kind of symmetric. Look at the first item and the last item. They are symmetric. Is anyone surprised that it is symmetric? And why is it symmetric? Okay. So let's look at the meaning of each row. Okay. This row is basically related to what if out of 10 coin tosses we got 0 heads and they're all 10 tails? And then the other one is asking what is the probability of tossing a coin exactly 10 times, but this time we get 10 heads and 0 tails. Don't you think the probability of those two should be about the same when the coin is not loaded? Because when the coin is loaded, it's going to favor one instead of the other one. Okay, so assuming the coin is not loaded, which means the probability of landing on the head is 50% and the probability of landing on the tail is also 50%, it is not surprising that these numbers are symmetric. The second question is, when we plot this, okay, when we plot column C against column A, what should we see? Okay, that's the next question. So we'll go ahead and try to do that. Okay, so we'll plot that up. Okay, so I think it's shift here, control click, and then control shift click. There we go. All right, so then we can now insert a graph. You can see that I don't use a spreadsheet very often. Insert chart. There we go. And okay, let me pull this screen over here so you can see how I set this up. I will make this a XY scatter chart. I could have just used a bar chart. It will work out exactly the same way because column A is linear, and so it doesn't really matter whether I use a bar chart or an XY scatter chart. But since I set it up to be like this, might as well. And I can make it use lines, and well, we can smooth. Okay, so everything looks a little bit better this way, and then click finish. What does that look like to you? Sort of like a bell, doesn't it?
Yeah, bell curve.
Yeah, it looks like a bell curve. It's not really the bell curve. It is the approximation of a bell curve because the function itself is discrete. Okay, when you look at the x-axis, the x-axis is actually discrete here. There's no 0.5. There's no entry corresponding to 0.5 because you cannot end with half a head with a coin. Does that make sense? But when you look at the shape, it does resemble the bell curve, of statistics. If you have not taken statistics, it's okay. Okay, it's not essential, but it is kind of important to notice this. Okay, so when we increase the number of n, the curve will start to look more and more and more and more like a normal curve. Okay, so I just want to point out that this is what we call the binomial distribution. It is related to the bell curve that you see in statistics. Okay, so I just want to point it out. We're not going to get too much into that aspect. Okay. All right. So now the question is, what if the coin is not is loaded? Then how do we compute the probability? It becomes a little bit harder. Okay. So in that case, what we'll do is we use this thing over here, okay? Because what P is representing is if the coin is loaded, which means one side is heavier, so that whoever is playing the game can basically cheat. Okay, so if P is represented of by the if P is representing the chances of landing on the head, then Q is representing the chances of landing on the tail. So because a coin can only land on a head or a tail, so Q is just 1 minus P. So do we have any questions about why Q is 1 minus P? Because Q is the chances of landing on the tail, and when you are flipping a coin, it has to land on either a head or a tail. Okay? Then we look at this, this formula, which doesn't seem to be very important. Okay? We're looking at this part here first. Okay? So let me try to highlight just the portion that I want. There we go. Okay, so if we focus on just this portion over here, you go like, Tech, don't we already know the answer of this expression is 1? Yes, we do, okay? Because P plus Q is by definition 1. 1 to the power of 5 is obviously 1, okay? So why are we interested in this? Well, we are not really interested in that part, okay? What we are interested in is how do we express P plus Q to the power of 5? So as it turns out, this once you expand it, it becomes a form that can be summarized using this sigma notation. There'll be 6 terms, okay? So we'll have term 0 up to term 5. Term 0 is basically just replacing I with 0 all, in this sub-expression here. So k of 0 is just a constant. We'll figure out what k of 0 is later on. But then the rest of it is p to the power of 0, q to the power of 5. When I equals to 1, then we have k1, which is different from k0. And then we have p to the power of 1, q to the power of 5 minus 1, and so on. Okay? So, but when you look at this one here, it is representing, I is the number of head, and 5 minus I is the number of tails. So p to the power of I times q to the power of 5 minus I is the probability of landing on the head I times and landing on the tail 5 minus I times if you just flip a coin 5 times. Okay? So if we know that one already, what is ki doing here? Ki is trying to say, well, if you want to land on the head once and land on the tail 4 times, okay, this portion will give you the probability of that. But then the question is, how many ways can we do this? Oh, there are 5 ways to do this, because we can have head and then 4 tails. We can have a tail, head, and then 3 tails. We can have 3 tails, 1 head, and then 2 tails. We can have 3 tails, 1 head, and then 1 tail. Then we can have 4 tails, and then the last one is a head. So ki in this case, or k of 1, should be a 5. Okay? So from this observation over here, we kind of have an idea of what ki is going to look like, don't we? What do you think k of I should look like? No one? Okay. K of I is 5 choose I. So this k of I over here, the constant or the coefficient, is just 5 choose I. So when you expand this, what do you think this is going to resemble? So before the end of today's lecture, we're going to close up soon. Okay, I know we are already over by 2 minutes, but I do want to go get over this entire subsection. Okay, so let me just give you a picture so that you can get an idea of how things are related, even though they do not seem to be related. Okay, all right. So I will use this format over here. So we got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Is anyone starting to recognize what I'm trying to construct here?
sense.
Sorry.
Fibonacci. Oh, yeah.
Pa-
Pascal's triangle.
Pascal's triangle. Okay. So we'll work this out until we get 5. Okay. So we have this is 0. This is 1. This is 2, 3. This is 4. So you can see how each number is really the sum of the one on top of it and the one on top and to its left. Okay, except for the one at the very first part. So we got a 6, we got a 4, and then we got the last one here. And then we have a 1, 5, 10, 5 again, 10, 10, and then a 5, and then a 1. So this is the row that we are interested in because, hey, that really kind of describes what we should be expecting with our k of I. So if I were to fill in these k's of i's, they would be k of 0 is 1, k of 1 is 5, k of 2 is 10, k of 3 is 10, k of 4 is 5 again, and then k of 5 is 1. Okay? So now we can start to see, so are we saying that the Pascal's triangle is in some weird way related to combinations? Is anyone having that question? Because I think that's a pretty natural question to ask, because we are looking at combination over here, and then we are looking at the coefficient in a binomial expansion, and then we look at the Pascal's triangle and go like, yeah, we know how to use Pascal's triangle to solve for k of I, but now we also know k of I is a combination, so those things are all related in some, well, I would say kind of weird, but really mathematically speaking, not too weird way. That's what the rest of the module is going to explain, is why are they related? How do we use Pascal's triangle or Pascal's identity, and also later on the binomial theorem to show that this is the Pascal's triangle, and it does give you the combinations. So this is what we'll do next Monday, because on Wednesday we'll have our exam 2. So exam 2, I can give you guys a few more exercises for exam 2 because I got my program working. So it's generating various cases for you guys to look at, especially when it comes to CNF questions. So we'll go ahead. So I will post some additional exercise questions for that.
Cool, that'd be awesome. Thank you.
Yeah, absolutely, absolutely. I spent the entire break writing code to generate questions for exam 2, not only for this class but also CISP 310. So it was good. It was a good break for me. Cool. So I'm gonna sign out now, from the voice channel and also the live stream, but I will still be looking at the text channel. So if anyone has any questions, don't hesitate to ask using the text channel. Uploading the mousepad to Canvas, sure. So I'm just gonna copy this and put it onto the Canvas. I'll put it into the announcements. You're welcome. Alright, so today's date is 2020-0413. This is just from the text part of it. So it's not going to be very helpful without the context of the lecture, but it's still useful if you watch the whole thing. Okay, click save. There we go. All right. So I'm going to sign out now, and I will go ahead and find time to grade the last question so you guys have an idea of where you stand in class. I also heard from the state chancellor, somewhere in the news, but you guys probably need to confirm it first, is I think the state chancellor's office is allowing people to retake a class in the fall because of the impact of COVID-19. I'm not 100% sure about the validity of that news, so I will dig a little bit before I say another thing, but you guys might want to dig into that too, because that might give some people certain options. that was not previously available. So I would just use that to conclude today's lecture, and then I'll give you guys instructions of how to get started with exam 2 before the exam 2. So I will give you some instructions tomorrow so that you guys can prepare can better prepare yourselves for exam 2. All right. So I'm gonna sign out now from Discord and then from the YouTube live stream.